Okay. I think we are. Yeah, we're looking good. All right, good shit. All right, so hello everyone. Welcome. This is going to be a correction stream. We're going to be revisiting the Karatsuba Multiplication Algorithm, but this time we're actually going to be doing the correct version because last time there were just a lot of things that I did wrong in terms of the indices and the array divisions, or the array splicing, all that stuff. And I figured instead of just linking to another video, because there were already plenty of links to GitHub commits that just pointed nowhere, I might as well just redo the entire thing in an accurate manner, actually. So we're going to be walking through the whole algorithm once again. We'll just be redoing the lecture right now. All right, so let me show a desktop, and I think we should be good. Yeah, we are looking good. All right, so yeah, so the Karatsuba multiplication algorithm is a divide and conquer algorithm that will allow us to speed up the way that we multiply different integers, or multiply big integers, and it's going to be directly applicable to our situation since we represent our big integers using integer arrays. So we'll be treating each digit, and we'll be splitting it up, and we'll see how we'll do that right now. So let's look at a general multiplication. So let's say we have x. This is x. And then we have y down here. And we want to multiply these two numbers, so x times y. And for sake of simplicity, let's assume that they are each n digits long. So the divide and conquer algorithm, the way we're going to apply divide and conquer here, which as the name suggests is just a template for dividing a problem into smaller subproblems that are in similar structure, and then solving those subproblems recursively, and then combining the solutions to get the solution to the entire problem. So divide and conquer in this case will involve dividing the digits x and y, or the numbers x and y, into two digits, where each digit, or quote unquote digit, because we're going to treat it like a digit, but it may be composed of multiple other smaller digits. So this will be x1, x0, and y1, y0. So doing it like this gives rise to a representation of each of these numbers as polynomials. So if we have a base b, we can now write x as x1 times b to the n over 2, because that's the power of the digit at the beginning of x1, where x1 is just the magnitude of the digits, or the magnitude of the left half of the number, and x0 is the magnitude of the right half of the number. And this will be just plus x0 times b to the 0, where once again b is our general base. And then similarly, y will be y1 times b to the n over 2 plus y0 times b0. So when we multiply these, we're going to look at how we can multiply these polynomials here. So let's look at the polynomial division, and then we'll kind of put it in this table here. So when we have this times this, we're just going to do polynomial multiplication, which will be distributive, the FOIL, whichever way you want to do it. So we'll start with the largest two terms. So we have x1, y1, b n over 2, b n over 2, plus x0, y1, b0, b n over 2, plus x1, y0, b0, b n over 2, and then finally plus x0, y0, b0, b0. So that's our polynomial expansion of this multiplication. And then if we simplify this, we get that x1, y1 times b to the n, plus, and then in parentheses x0, y1 plus x1, y0, and this will be times b to the n over 2, just by doing exponent multiplication. And then the last digit is x0, y0, b to the 0, but once again b to the 0 is just a 1, so we're just going to put it there for correctness, or just for the display here. So we have this representation here, and in our table what this will look like is we have this division, this digit, or this part of the multiplication, x0, y0 is going to be the first digit, or the first part. It'll be the lowest magnitude. So over here we have x0, y0, and this will start at, we start over here at 0, and we're going to put this as b to the 0 because that is essentially the weight of this digit. So this is at b to the 0. And then x0, y1 will be this one, this block. And that's at, let me move this down a little. And this, the weight of this digit is b to the n over 2. And then x1, y0 is a similar thing. And then finally x1, y1 will be the largest weight here. x1, y1, and this, the weight over here will be b to the n. So you can kind of see how the digits x0, y0, and then x1, y1, those multiplications do not overlap. However, there's this middle term here that will overlap. Now, if we were just to apply this, if we were just to do these multiplications all separately, we would get an O of n squared algorithm, which is no better than than long multiplication, which is what we're trying to improve here. However, if we do a few modifications here, so let's let a number low equal the x0, y0 multiplication, the high number equal x1, y1, and then we have our mid value, m, which is equal to just this number here. So we have x0, y1 plus x1, y0. I'll just use L, H, and M. So this then tells us that x times y is equal to h times b to the n plus m times b to the n over 2 plus L times b to the 0. But once again, this is just the same thing. We have not made any improvements. However, when we look at look at another form of m, so let's see. Let's just look at the multiplication of x1 plus x0. This polynomial times y1 times y0, or y1 plus y0, where these are just the equivalent sums of the two halves of the number. So what we're going to get here is this is equal to x1 y1 plus x1 y0 plus x0 y1 plus x0 y0. And you may recognize this as exactly what we have up here, except there are no powers applied to these digits. However, this still helps us because we can see this as x1 y1 plus x1, or we can then apply our variables here, and we'll see that this is going to be h plus m plus L. Now, if we want to get m here, all we have to do, then therefore m is equal to this multiplication, x1 plus x0 times y1 plus y0 minus h minus L. So now we have a simplified form for m, and we only get it through one extra multiplication, because h and L will already be computed using respective multiplications. So rather than having 4 multiplications, we have 3 multiplications, which gives us a running time of O to the n of log 3, which is better than, less than O of n squared. All right. All right, so that's the algorithm that we're going to be writing out today. All right, so let's hop into the code now. And we are going to start in cmathematics.h. And we're just going to delete this because we're going to write it right now. So we need to have one new macro here. One new macro function is just going to be #define min. And this just takes two numbers and returns the minimum. Oh, no. I don't know what that was, but I didn't, probably should not have showed that on the stream. So we want to return the minimum value. So we're going to say it's the opposite of max. So I1 is less than I2, question mark I1 colon I2. And this just returns the smaller of the two numbers. All right, so that's good there. Now for big int, now let's hop into bigint.h. And I just need to figure out what I need to actually do here because this should be a 9. Okay, so in bigint.h, there's a few things that we have to change, or we're gonna have a few things here. So we're gonna first make the base number of base digits 9 and make the base 1 billion, I believe. I changed that in the first version of this lecture, or of this stream. So if you haven't watched that, then you don't need to worry about this. This should already be just 1 billion and then 9 digits. All right, so that's that for maintenance. And then now it's actually, this I don't think we had either. Okay. Let me just make sure of this. Yes, okay. All right, so we only have our one constant so far. And then this function r also does not exist yet. Okay, so let's actually, so we looked through cmath.h and just added the min macro, and now we have another macro to create. So in some cases, you may be thinking, okay, well, yeah, this is much faster, or faster than long multiplication. However, don't we still need to like create all these arrays and splice all these numbers? And yes, that is exactly true. So we are going to have to be careful in how often we want to use Karatsuba. So we're going to kind of define a threshold between using Karatsuba multiplication and long multiplication. This is kind of similar to using quicksort, and it's similar to combining quicksort with I forget, with an O event squared algorithm. So in some cases, using quicksort, which is n log n, which is similar to what we have here, is actually going to be slower for lower values of n. So for example, or not for example, but yeah, that was the example. So we're going to want to define a threshold here to give us a boundary between when we want to use Karatsuba and when we want to use long multiplication. So we're going to have a macro up here. It's going to be #define Karatsuba threshold, and we'll define this as, let's say, 4. Just so for our sake we can kind of see both algorithms working in parallel. All right, so that's our new macro here. All right, now for some constants. We're still gonna keep the big or the general multiply big int method, but we're gonna have a few new ones. So in multiply big int, we're gonna want to have a few pre-checks based on if a number is 1 or -1 per se, and we can just quickly return the result without actually calling any algorithm. So we're gonna have two new constants. We'll have an extern const big int 1, and then extern const big int -1, just like that. And we can actually go ahead and define these in bigint.c right now. So we have our bigint 0, and we want to define our bigint 1 and -1. So we're going to have a const bigint 1, which is equal to, so for the sign we have true, then for the capacity we'll have 1, number of digits is 1. Now for the array we can't simply just put a 1 there. That doesn't work like that. I don't think it does, at least. Maybe it does, but I think this will fuck with, this will fuck with the compiler. So to get around this, we can simply just create a global integer array R1 of length 1, which is just equal to a singular 1 in the 0th spot there. And we can just pass in this array R1 as the digit array for bigint 1 and bigint -1. And then similarly, bigint -1. Now this is going to be equal to false for the sign since it's -1. Capacity is 1, number of digits is 1, and then we can still use the same digit array since it's still the same magnitude. So just R1. All right. We're actually going to make this threshold 5, just because this will just make it a little easier. All right, so we have our constants, and then we have one helper method that we're going to write, and then we will actually get into the algorithmic code here. All right, so this new method is going to allow us to copy a big integer, or copy an array, an integer array as a big integer into an integer. So we're going to, in bigint.h, we're going to have a definition. It's going to return a bigint, and it's going to be copy integer array. We will pass an integer array, an integer pointer, an unsigned integer n for the number of digits, and then the boolean for the sign. So since we want to, since this is going to be a recursive algorithm, I'm gonna want to avoid the overhead of instantiating all these big integer structures. Rather, when we can simply just work with the integer arrays and have the same result, because the signs don't determine how many digits there are. The multiplication result only depends on the magnitude. So we'll do the multiplications based on the integer arrays, and then we will copy that final result into a big integer structure, which just allows us to avoid overhead. Alright, so as for the definition of this method, just gotta find the reference real quick. Here we go. Alright, so I'm going to copy this signature, and then we're going to put it in over here. So for copy integer array, we're first going to get our return integer. So big int ret is equal to allocate big int, and the number and the capacity will be n for the number of digits, just because we want to allocate that memory right now. And then we're going to say ret.number of digits is equal to n, ret.sign is equal to sign. the sign that we passed in, and then we're going to copy over the array. Turn this down a tad. So we're going to copy this using memcopy. So memcopy, the destination will be ret.digits, the source will be array, and the number of bits to copy will be n times the size of an integer. Like so, and then we just want to return ret at the end. Alright, so that's copy integer array, and we're going to be using this method when we write the actual multiplication methods. Alright, let's go back into bigint.h, and we are going to have we're going to have some new methods here. So let's scroll to the bottom. We're going to keep our multiply bigint method. This will be our general method, and from this method we're going to decide which algorithm to use. Once again, because we're going to have a threshold based on if we want to use the Karatsuba or long multiplication algorithm, whichever one. It just depends on the number of digits, essentially. So we're going to have 4 new function definitions. It seems like a lot, but it'll make sense. Alright, so the first one is going to be big integer return, long multiply big int. And we pass in big int I1 and big int I2. Alright, and then we're going to have a lower level method called, and it's going to return an integer pointer, so an integer array. It'll be long multiply integer array. So this method will simply just just multiply using the long multiplication algorithm 2 integer arrays as if they were big integers, but once again we're going to avoid the overhead. So we're going to pass an integer pointer I1, and then we're going to pass in a range. So unsigned integer I1, unsigned integer I1f. So this should be I1i and I1f. And then we're going to have a second integer array, integer pointer I2, an unsigned int I2i, an unsigned int I2f. And then we want to output to a size. So we're going to return an integer pointer as an array, but we also want to return the size of the array, because we may have some zeros at the beginning that we don't want that we want to just trim off. So we'll have an unsigned integer pointer out size. And this will just be a return value that is implicitly returned when we assign to it in this function. Alright, so those are the 2 long multiplication functions. And then now for the Karatsuba. So it's going to be the same structure. We're going to have one for the structures and then one for the integer arrays. So we're going to have a big integer return, Karatsuba multiply big int. Pass in a big int I1 and big int I2. And then we're going to have a method that returns an integer pointer, integer array. It'll be Karatsuba multiply integer array. Here we're going to pass in an integer pointer I1, an unsigned integer I1 size, so the size of the array, an integer pointer I2, an unsigned integer I2 size, then an unsigned integer IDXI, unsigned integer IDXF, and then like the long multiply integer array, we're going to output to a size, so unsigned integer pointer out size. Alright, so let me explain these parameters. So I1 is going to be our array. I1 size will be the size of the array. I2, same thing, and I2 size is the size of the second number. Now IDXI and IDXF represent the division of the numbers that we're looking at currently. So one way that we can make this algorithm more efficient in terms of memory allocation is just simply we don't have to copy each half of the halves of the numbers into separate arrays. We can simply just narrow the scope that the method looks at. So for example, if we're looking at these two, and let's say they have n is equal to 8 in this case. So for the first call, when we want to find h, or the high, we're going to call Karatsuba when IDXi is 4 and IDXf is 8. So the second halves of these digits, this half right here. And then for the low value, we'll be calling it from 0 to 4. So we only want to look at the lower half of each array. And this just allows us to avoid creating too many new arrays. And also notice here how, unlike long multiply integer array, where we have different ranges, this range here will be global. This is important because the range, this range has to be parallel to both integers. We can't use half of one integer, like let's say if x had 8 digits and y had 4 digits. We can't consider y1 to be from y2 to y, or we can't consider the higher half of y to be the second and third digits of y. It has to be the 4th, 5th, 6th, and 7th digits, which will just be a 0. So for example, let me just plug this tablet back in real quick. So if x is equal to, and I'm going to be, so this will be 10, or b to the 0. So we have 0, 1, 2, 3, 4, 5, 6, 7. And then y is equal to 0, 1, 2, 3. So we're going to choose our value n to be the maximum of xn and yn, or ny and n, or nx and ny, which is the max of 8 and 4. So this is going to be 8 here. So our divisions now have to go straight down the middle of n equals 8. So this division right here. So therefore, x0 will equal 0, 1, 2, 3. x1 will equal 4, 5, 6, 7. And then y0 will be all of y. 0, 1, 2, 3. We can't split up y right here because these halves don't match. That will not give us the correct result of the multiplication. This division has to apply to both. And then y1 would just be all zeros. Because implicitly we have zeros here. It just doesn't affect the magnitude. And then another kind of way that we can make this more efficient is instead of padding to get zeros to the same length, we can simply just determine if indices are greater than the size, and if they are, then we can just implicitly put a 0 wherever it's needed. Alright, so these are the 4 methods that we're going to be working with today. Alright, so let's copy our signatures, and let's paste them in at the bottom of bigint.c. Alright, so we're going to start and multiply bigint here. So in multiply bigint, we are first going to compute the sign. And the sign will just be the result of the XNOR of the two signs. So Boolean sign is equal to not of I1.sign XORed with I2.sign. So if the signs are the same, then it's going to be a positive result. And if they are different, then it's going to be a negative result. So that's why we have the XNOR. Now we're going to get the result. So we're going to, oops, what did I do here? Oh, sorry, this is wrong. I was jumping the gun. This is not, we don't want to do this yet. So in multiply bigint, we're going to have some simplification checks. So we first want to determine if either is 0. So if either is 0, return 0. So if not compare big int I1 big int 0 and so not, and then in parentheses we're going to have compare big int I1 and big int 0 and compare big int I2 and big int 0 here. So I applied a bit of De Morgan's law here, so this would read not compare I1 to big int 0 or not compare big int I2 to 0. Just because if the comparison returns a 0, then they are equal. So we're just going to apply De Morgan's law and get that this will just be not of these two ANDed. Because if one of them is 0, then this whole AND will be 0. So at least one is 0, and then we just not this to 1, so it goes into this if block here. And in this case, we're just going to return big int 0. Alright, now we're going to compare to positive and negative 1. So if either number, we don't need to do this. Sorry, this is a useless comparison here. Or is it? No, it's not. We're just going to compare each number to 1 and the negative 1. So if either number is 1, then copy the other digits, keep the sign. And then if either number is negative 1, copy the other digits and reverse the sign. So that makes sense. Anything times 1 is the same number, anything times negative 1 is the opposite. So same magnitude, just different sign. So now we're going to do this again. So if, more De Morgan's law, so if not, and then in parentheses, we need to make these comparisons first. So character I1 comparison, we're going to compare this to positive 1. So this is going to be equal to compare big int I1 to big int 1. And then char I1 comparison to negative 1, which is equal to compare big int I1 to big int negative 1. So then if, more De Morgan's law, if not I1 comparison P1 and I1 comparison N1, so if either of those are false, then we're going to return copy the integer array. So we're going to copy over memory. The source array will be I2.digits, because I1 is 1 or negative 1, so we want to copy the digits of I2. The number of digits is I2.number of digits, and then the sign will be not I1 comparison P1, or we can actually just say I2 or I1 comparison N1 question mark I2 dot sign, or sorry, question mark not I2 dot sign colon I2 dot sign. So the reasoning behind this ternary operator here is the sign will be reversed if the comparison to negative 1. Oh wait, this is wrong. The condition here should be not I1 comparison to positive 1. And if that results in true, we'd want to return the original sign, and if it's not true, we want to return the opposite sign. Yeah, just like that. And then we're going to do something similar for I2, comparing it to positive and negative 1. So character I2 comparison P1 is equal to compare big int I2 to big int 1. Character I2 comparison P2, or N1, is equal to compare big int I2 to big int negative 1. And then the same if statement here. I'm not gonna copy it, but I'll just read it out again. So if not, then in parentheses I2 comparison P1 and I2 comparison N1. So if either of those are false, then we're going to return the copied integer array. We're going to copy I1's digits. We're going to copy I1.number of digits. This is misspelled. And once again, the same reasoning for the sign, or the same calculation for the sign. So if not, I2 comparison P1 question mark I1 dot sign colon I2 dot sign, or not I1 dot sign. So once again, if the comparison of I2 to -1 returns 0, then I2 is -1. So in that case, we would want to reverse the sign, which gives here, and if it is +1, then we want to return the original sign of I1. Okay, so now that we have got our base case, or our checks out of the way, we can actually determine which algorithm to use. So we're first going to get the maximum and minimum number of digits. So unsigned integer minimum number of digits is, we're going to say, is equal to I1.number of digits just by default, and then unsigned integer maximum number of digits is equal to I2.number of digits, and then if I1.number of digits is greater than I2.number of digits, then we just want to reverse them. So minimum number of digits is going to be I2.number of digits, and then max is going to be I1's number of digits. So once again, when we use this algorithm, we need to determine the maximum number of digits as kind of our bounds for the initial call to the algorithm. So that's why we need the maximum here. All right, so now let's determine which algorithm to use. So we're going to have a little bit of a cheeky thing here. We're going to have one more check to determine. So let's just revisit what the complexities here. So long multiplication is O of n times m, where we have n is x is the number of digits of x, and m is the number of digits of y. So this is just the complexity of long multiplication, and let's assume that n is greater than or equal to m. Now for the Karatsuba, we have that O of max, so the complexity is O of the max of n and m to the log of 3. And this is equal to, the O of n to the log of 3. Just because we know that the max of n and m is just n, since we know that n is greater than or equal to m. And this is approximately equal to O of n to the 1.585, and we can approximate this to O of n to the 1.5. Now if we want to do a comparison here, we want to use long multiplication when n times m is less than or equal to n to the 1.5. So whenever this condition is satisfied, we will know, or we can reasonably assume that long multiplication will give a more efficient result than Karatsuba. So if we do some algebraic manipulation, we get that m must be less than or equal to n to the 0.5, which is why I approximated it to that, which is equal to the square root of n. So now we have two checks here. We're going to say if the maximum number of digits, or if the maximum number of digits is less than Karatsuba, the threshold, the macro that we had, or minimum number of digits is less than or equal to the square root of maximum number of digits. Yeah, and we're just going to take the square root of, we can just use the L just to make this an integer so the comparison returns the correct result. I am already out of water, that's unfortunate. Alright, so in this case we're going to do long multiplication. So return the long multiply of big int I1 and I2. Else we're going to return Karatsuba multiply big int of I1 and I2. So we're just calling the base, these are the initial calls to each algorithm. Alright, so let's go through long multiply big int first. And then because we need to rewrite the integer array multiplication here to kind of suit the new parameters. So just wipe whatever we had for the long multiplication, and then we're going to rewrite it completely. Alright, so for the long multiply big int, so the overhead, so the general call, we're going to first compute the sign using XNOR. So Boolean sign is equal to not of I1.sign XORed with I2.sign. So XOR will return true if I1, if only one of these is true. And in multiplications, if the signs are different, then we have a negative result, and if they are the same, we have the positive result. So we want this to be false when only one of them is positive and one is negative. So this will be the not of XOR, so XNOR. So now we want to get the result and insert into the big integer structure. So we're going to get an unsigned integer number of digits just as our placeholder for this parameter right here. We're going to say integer pointer ret array is equal to the long multiplication of integer of int r. So we're now going to the lower level method where we pass in I1.digits, and we're going to multiply from the range of 0 to I1.number of digits, and we will multiply this by I2.digits from 0 to I2.number of digits. And then we will output the size to a reference to number of digits. So this just means that we're multiplying through the whole range of both digits. And then we want to copy the result over. So big int ret is equal to copy integer array, where the array to copy will be the return array returned by the long multiplication. Then the number of digits will be the number of digits, and then the sign will be the sign. Alright, then we can do some trimming, so remove leading zeros. So trim big int, pass in a reference to ret. Then we want to free the temporary array. So free ret r, and then return ret. Or we can also just say if, or wait, no, never mind, we're good. Or just as another check, we should say if ret array, and then we should free the array. Alright, now for the actual long multiplication algorithm. So we have looked at this before. This was in episode 8, I believe. Could be wrong though. So the algorithm will pretty much be the same, except we have, there are going to be different indices now that we have a specific range we want to multiply through. So we're going to have some placeholders here, or just numbers. We'll have unsigned integer I1 range is equal to I1f minus I1i, so just the range in I1, the number of digits that we're multiplying by in I1, and then unsigned integer I2 range is the same thing for I2, so I2f minus I2i, and then unsigned integer number of digits is equal to just the addition of the ranges, so I1 range plus I2 range. Reasoning behind this last time, that's just how multiplication works. It will always output to a result that is at most the addition of the number of digits of the individual factors. All right, now for the allocation, we're going to have the integer pointer ret is equal to malloc. We're going to allocate the number of digits times the size of an integer. So we're just allocating an array here for the return. And if not ret, we're going to return 0. So dereference out size, set to 0, and then return null. All right, then we want to set all these to 0. So initially, we want to set all the digits to 0. And we can use this method memset. So the destination will be return. The value to set each character, not each integer, it's going to be each character, will be 0. And the size will be the number of bytes. So it will just be the number of characters in the array, which is the number of integers in the array times times 4, which is the number of characters in an integer. So it'll be number of digits times the size of an integer divided by the size of a character. So this is just for demonstration's sake, but this could also just be number of digits times the size of an integer. But we're just gonna just leave it like this just for demonstration purposes. Now, for the main loop, we're going to have our for each digit of I1. For unsigned int I is equal to 0, I is less than I1 range, I++. Then we're going to have our carry, integer carry is equal to 0. Then for each digit of I2. For unsigned integer j is equal to 0, j is less than I2 range, j++. So some similarities and differences. We still have our I and j as our counters for each digit, or for each factor, but this time we are going to I1 range and I2 range, which is similar because last time we went to I1 number of digits and I2 number of digits, except this time it may not be the whole number that we're iterating through, so we only want the ranges to go up to the ranges. All right, so we want to get the product here. So the multiplication of the individual digits. So big integer product is equal to multiply int. So this will just get the, we want to handle some overflow. So if the multiplication of two larger integers overflows into a second integer, then we want to handle that. So we're going to multiply these in I1. The first digit will be I1 at I1i plus I. So we're going, so in the digit that was, in the first digit that was passed into, or here, let me just diagram this out real quick. It'll be easier to explain. There we go. So let's say we had x is equal to 0, 1, 3, 4, 5, 6, and y is equal to 0, 1, 2, 4. And we call long multiply on x from 2 to 4 and y from 1 to 3. This will likely never happen, but just for a demonstration. So we want to go from 2 to 4 and then 1 to 3. We're non-inclusive, actually. So I'll just make this 1 to 4 and then 2 to 6, just to make this like that. So the first digit, or we're going to start our counter I at 0. When I is equal to 0, we want to be multiplying x of 2. So so this is equal to x of I plus 2, which is equal to, or 0 plus 2, which is equal to x of I plus I, or xi. So we're going to start our counter from the first digit, but the index of that first digit is the parameter. So we can't just use I, we need to say I plus I1i. So we're going to multiply that digit times I2 at I2i plus j, similar reasoning. Now this is another error that was in the last video, or the initial the initial stream. There could be two possible overflows here. And I only found this when doing a random example, and I'm happy I did, because otherwise that would be an error that I did not catch. So there could be an overflow just in the when adding to, let's say we have the value, or our current digit at ret at I plus j already has a value, and then we add the result from the product, which could result in an overflow, but then also the carry has another value that could result in a second overflow. So the first step will be to calculate the additional contribution to the current digit. So we're going to have an unsigned integer addition is equal to 0. Yeah. Now, or we can actually just set addition to carry. So if product.number of digits is greater than 0, sorry about that. So where we were, if the number of digits in the product, let me just make sure this is going through. Yeah, okay. So if the number of digits in the product is greater than 0, then we have a result from the product. So we're going to say addition plus equals product.number of digits, or plus equals product.digits at 0. Now, we are also going to calculate a possible carry from the contribution. So if the addition is greater than or equal to base, then we have an overflow. So carry is equal to 1, and then addition minus equals base. This is just, we know what this is. This is just in our addition, so if the number is greater than the base, then we just want to have the carry set to 1 and then subtract from the base. And otherwise, carry is equal to 0. Alright, next we are going to assign to the digit. So ret at I plus j plus equals the addition. Once again, we're doing a plus equals because there could already be a value from our previous multiplication. Alright, then we want to determine the carry, calculate a second carry. So if ret at I plus j is greater than or equal to the base, then carry plus plus, and ret at I plus j minus equals base. Once again, same kind of thing here, except this time we're doing carry plus plus because the carry could already be 1. And then we want to add the carry from the product. So we're simply going to say carry plus equals product dot digits at 1. Oh, we need to have an if statement here. So if product dot digits is equal to 2, then, or is greater than 1, then we will have an addition to the carry here. And then outside of the inner loop, we're going to deal with the leftover carry. So if carry, then ret at I plus I2 range is plus equals carry. And this is just the carry from the last digit over. And then the last 2 lines of the method will be, we're going to set the outsize, so dereference outsize and set it equal to the number of digits, and then return ret. Just like so. Alright, so that's the new long multiplication method. I'm going to go refill my water because I'm losing my voice, and then we will move on to Karatsuba in just a second. Don't worry, boys. I'm back. Man, this album fucking slaps. I've been listening to this way too much in the past few streams. I don't want to get sick of it. I don't think I will. But I probably should moderate how much I listen to it. Alright. Alright, so let's move on to Karatsuba Multiply Big Int. Now this is going to be pretty much the same format as long multiply big int, where we kind of just make the call to the lower level method, copy the result over, and then trim and then free the temporary array. So for Karatsuba Multiply Big Int, we are going to calculate the sign again. So compute sign using XNOR. So boolean sign is equal to not I1.sign XORed with I2.sign. Then we're going to determine the maximum number of digits. So unsigned integer maximum number of digits is equal to the max of I1.number of digits and I2.number of digits. So once again, we looked at this. When we call this method initially, we need to get the maximum of both numbers of digits, and that will be our global bound for the algorithm. Then we're going to get the results. So we're going to have our placeholder unsigned integer number of digits, and we're going to have an integer pointer return array, which is equal to Karatsuba multiply integer array. pass in I1.digits, I1.number of digits. So once again, we pass in the sizes of both arrays and then the global bounds after that. I2.digits, I2.number of digits, then 0 to maximum number of digits, that's our global bound, and then our other return value, which will be number of digits. And then we're going to get our return structure, which is equal to copy integer array as above. And the digits to copy will be return array, number of digits, and then the sign will be the sign. Then we want to remove the leading zeros. So trim the big integer, pass in a reference to ret, and then free the temporary array. So free return array, or if return array, then free return array, and then return ret. All right, now for the actual algorithm. So this is just our upper level call to the algorithm, and now we're actually going to be looking at the divide and conquer structure here, which is going to be fucking cool. All right, so as with the highest level method, as with multiply big int, so where we haven't specified which algorithm to use yet, we are going to need to have a few checks first. So the first one will be, I don't know why this is there. So if some bound checking. So if IDXI is greater than or equal to I1 size, or IDXI is greater than or equal to I2 size, or IDXI is greater than or equal to IDXF. That will never happen, but just in case. In this case, it's going to be 0. So out size is going to be equal to 0, and then return null. So we dereference out size, set it to 0, and then return null. The reasoning behind this is because if we look at this example again, the first call to multiply the higher number of digits will give us a 4567 or a 7654 times a 0, which will just result in a 0. And we know this, we can already determine this because the initial index of the current range is greater than the number of digits of y, so or greater than or equal to. So we have 4 is greater than or equal to 4. The initial index of the range, which is 4, is greater than or equal to the size of y. And then this third one will likely never happen, but just in case. All right, now we're going to have some values to help us with indexing. So we're going to have our range, unsigned integer range, is equal to IDXF minus IDXI. Notice here how we only have one range instead of two ranges because we have one global range of indices. And then we're going to calculate the number of indices or number of digits in the return. So unsigned integer number of digits is equal to range left shifted by 1, which is equal to range times 2. And this is kind of just similar reasoning to the size of the product, but this is just assuming that both numbers have the same ranges in this call, but that may not be the case, but we're just going to create the space for it. All right, then we're going to have a half here, so unsigned integer half, and this will be our mid index. So the splicing index. So this is going to be equal to the average of the two. So we're going to say IDXF plus IDXI, right shifted by 1, that's just the average, and then we're going to add 1 if range is odd. So plus, then in parentheses, range ampersand with 1. So this is just equivalent to the ceiling of the average of IDXF and IDXI. And we want to add 1 if the range is odd which you can determine with this operator right here. And then unsigned integer sum term size. So the size of each sum term, because if you remember, when we're calculating the middle term, we get the sums of the digits of the halves of each number. So we need to determine how many we're actually going to have to allocate the arrays for these sums, just because we can't hold it anywhere else or in any existing spot. So we'll just do that. So the sum term size, this will equal half plus 1 minus IDXI. So the half plus 1 is just giving us, well, first of all, half minus IDXI gives us halfway through the range, or it gives us half of the range, I think. Yeah, it gives us half of the range, but then we want to add 1 for a possible overflow. Alright, now for divide and conquer, this is going to be the first element of the divide and conquer that we'll be coding. It'll be our base case. So at some point we want to stop the recursion. That's just an element of a recursive algorithm. So our base case will be do long multiplication if under the threshold. So if range is less than or equal to Karatsuba threshold, then we're going to return long multiply integer array. So we are going to the lower level long multiplication method since we don't have any structures to deal with. And we're going to multiply I1 from IDXI to the minimum of I1 size and IDXF. And then I2 from IDXI to the minimum of I2 size and IDXF. And the return will, and the output size will be an out size. So going from IDXI is just simple because that's the global range that we want to look at. However, with the minimum, the reason why we're taking the minimum is because we don't want to go beyond any ranges here. So if the final index, if the global index is greater than the size, then we don't want to multiply those digits. So we just want to essentially skip over them or imply that they are 0, which is just equivalent to stopping it at the end of the array. All right. Then after this if statement, we can proceed. So we're going to first allocate. So integer pointer ret is equal to malloc of number of digits times the size of an integer. Then we're going to allocate the sum terms, or calculate the sum terms. So integer pointer I1 sum is equal to malloc of sum term size times the size of an integer. Then integer pointer I2 sum is equal to malloc of sum term size times the size of an integer. These are both the same size. And then we're going to use parallel pointers to iterate through the two halves of both of our numbers. So we'll have an unsigned integer left IDX is equal to IDXI, and unsigned integer right IDX is equal to half. So when calculating the sum terms, this is what it would look like for our example here. Or actually, do I have an example in text? I think I may, actually. I do. No way. That's amazing. Okay. So, I just haven't used this. Okay. That's kind of stupid. But yeah, so when in this example here, we have a 3x3, which would be calculated using the base case. However, we're just going to assume not here. So just for demonstration's sake, the sum will be just the corresponding terms. So the two halves of x here are going to be these two digits as the first half, and then this one digit as the second half. So for the sum, we're going to take the first digit of the first half and the first digit of the second half and add them, and then for the second digit of the sum, we're going to take the second digit of the first half and the second digit of the second half and add them. However, there is no second digit of the second half, so we just add a 0 implicitly. So that's how we're going to do this. And in this case, since we're doing addition, we need to have some carry values. So Boolean C1 is equal to false, and Boolean C2 is also equal to false. So we're going to do addition as we have done before. And it's just easiest to avoid the overhead here instead of creating a new structure and then calling addition on those structures. So we're going to have a for integer I is equal to 0. I is less than the sum term size. And then for the increment step, we're going to increment I, left IDX, and right IDX. So I will act as our state variable here. This is going to be the counter of the index here. So we don't want to go above the sum term, above the number of digits in the sum term. And then since we're using parallel pointers, we need to increment those individual indices as well. Now for the addition algorithm, we've seen this several different times now. So just make sure this is going to, yep. So I1 sum at I is equal to C1, and C1 is equal to false, so reset the carry. Then if left IDX is less than I1 size, and left IDX is less than half. And in this case, we're going to say I1 sum at I plus equals I1 at left IDX. So the conditions here, we want to make sure that the left index is in bounds, just normal, and then also the left index is less than half. So when we calculate our sum terms, in this case the sum term size is 3. However, we don't want to add this third digit to this as if it were in the first half. So in this example here, the first half is once again these two, and the second half is this digit, but the sum term size is 3. So if we didn't have that check here to make sure that the left index is less than half, then it would add all 3 of these digits as if they were the first half. So we need to make sure that that the left index is not iterating beyond half. And this will happen because the sum term size is 1 more than half. Just for the additional carry. And then for the right side, we're going to say if right IDX is less than I1 size and right IDX is less than IDXF, then I1 sum at I plus equals I1 at right IDX. So the first condition here is the same. We need to make sure that it's in bounds, but then also we need to make sure that it's in bounds of the global array, because we could be focusing in on a certain spot or a certain range of the number, but because we are not copying all our digits over, there may be additional digits that we don't want to use. So we just need to make sure that the right index is also within the global bounds of our current iteration. Then we're going to do the same thing for I2. So I2 sum at I is equal to C2, C2 is equal to false, then the same conditions. If left IDX is less than I2 size, and left IDX is less than half, then I2 sum at I plus equals I1 at left IDX. Then if right IDX is less than I2 size, and right IDX is less than IDXF, then I2 sum at I plus equals I2 at right IDX. This should actually be I2 sum plus equals I2 at left IDX. In there. Alright, so same stuff there. Now for the carry. So if I1 sum at I is greater than or equal to base, then C1 is equal to true, and then we subtract the base. I1 sum at I minus equals base. This is traditional elementary addition. I'm actually just going to put this up here. If I2 sum at I is greater than or equal to base, then C2 is equal to true, and I2 sum at I is minus equals base. Alright, so now we have calculated the sum terms and we can do our recursive calls. Alright, so the first thing we want to have is placeholders for the sizes of each individual term. So unsigned integer, high size, mid size, and low size. Then we're going to actually make our calls. So we will have return types of integer arrays. So integer pointer high is equal to Karatsuba multiply integer array, so calling the same method. We will call this on I1. And I1 size is still I1 size, same stuff. I2 and I2 size, same stuff. Now for the new global bounds, we are going to iterate from half to IDX half. So the second half of our current range. And then we will output the size to high size. Integer pointer low is equal to Karatsuba multiply integer array. I1, I1 size, I2, I2 size. Now the range in this case will be from 0 or IDXi to half. And then the out size will be low size. And then integer pointer MD is equal to Karatsuba multiply integer array. This time we're going to be multiplying I1 sum, which has a size of sum term size. I2 sum, which has a sum of sum term size. Then we will iterate from 0 to sum term size, the entire digit or the entire number, and then output to MD size or mid size. Right, so those are our 3 recursive calls. I'll leave that there. I will leave that there for a second. So one thing that I probably could have said when I was looking at the sum terms is, whenever we're doing our additions and assignments to the return value, we're going to have 2 conditions always. There will always be 2 conditions for our index here. There's going to be the condition that that the index is within bounds of the array that we're looking at, but then also that the index agrees with the global bounds. So in this case, in this condition up here, we have that left index must be less than I1 size. So that's the array condition. It has to be less than the current array size. But then this is the global condition, where the left index must be less than the half of the global range. So that's kind of how I was thinking about this. So we will see this, the 2 condition format, when we do the other stuff here. So the next steps here is going to be to attain the middle term through subtractions. And we know that the net result will be positive, so there's no need to worry about the last carry. So we'll have an integer for our carry, which is equal to 0. Then for unsigned integer I is equal to 0, I is less than MD size, I++. So we are essentially just iterating through all the digits of MD right here, and we're going to be subtracting high and low. So we're going to say MD at I minus equals I, the first thing is going to be MD at I is equal to MD at I minus high at I minus low at I. And we're going to have 2 ternary operators in here. So MD at I minus equals, then this will be the sum of the 2. So this is equal to MD at I minus, then in parentheses, high at I plus low at I. So the first ternary will be I is less than high size to make sure it's within the high bounds. Question mark, high at I, otherwise subtract a 0 in its place. Then plus with I is less than low size. Question mark, low at I, and then 0 otherwise. Just like that. And then if carry MD at I plus equals a carry. And then we set the carry equal to 0, and then calculate the carry on the next digit. So while MD at I is less than 0, carry minus minus, and then MD at I plus equals base. And we've seen this before. So once again, this is a subtraction algorithm that we have seen several times before, or we have seen this before. All right, so that is the divide and conquer part. Now we have to combine, or sorry, we started with the combination. This is the divide and this is the conquer part where we conquer the divisions. This is the divide part. Right here, this is all the divide where we calculate the ranges, all that stuff. That's division. This is conquering. And then this is combination. All right, so for iterating and assigning to our output, this is kind of what the format's going to be. So we're going to have our output array, which will be, let me actually just do this in one note. Where's my pen? Oh, here it is. So we're going to have our, let me actually just copy this real quick. So in our output array, we have x times y. We will iterate from 0 all the way to n to input the low. So this will be low. And then n all the way to 2n to input high. And then we will iterate from n over 2 to 3n over 2 to input MD. So n over 2 to 3n over 2, and this will be an incremental step, so plus MD. So these results will all, that's going to be how we just iterate through this stuff. Let me just. So we're first going to calculate an integer low half is equal to half minus IDXI left shifted by 1. So this is kind of the highest bound of the lower half of the so this is going to be our equivalent to n in this case. So this will be n. Except we can't just output the range or IDXF just because we have to just do this calculation here just to get the actual number. So we calculate the distance from half to IDXI and multiply it by 2. And then we have a counter. This counter will stretch across all 3 iterations. So int I is equal to 0. Then 4, empty first condition. I is less than low half, I plus plus. This will be the low term. And then we're going to say ret at I is equal to I is less than loSize, question mark, low at I, colon 0. So once again, we see our global, then local check. So our global check is to make sure that I is within the lower bounds here. But then also we need to make sure that the index is not out of the bounds of the array itself. So we go I is less than loSize to make sure that we get a value from the lower array, but then also that it is outputting to the correct bounds in the output array. But we want to go through the full thing. We don't want to stop when I is equal to loSize, because we want to output zeros if we don't fill up all the terms. Now for the high term, we're going to have an integer high IDX is equal to 0, just to iterate through the higher term. So for empty first condition, I is less than number of digits. Then for the increment step, it'll be I plus plus and high IDX plus plus. So we keep the counter from the initial loop, and we're just going to iterate continuing on from where that stopped. So this will be the high term. So similar reasoning, ret at I is equal to I, or high IDX is less than high size, question mark, high at high IDX, colon 0. So once again, the local check is right here, global check is right here. Now for the incremental step. So we're going to set our carry is equal to false. This variable comes from here. Just set it equal to 0 or false, either one. Then unsigned integer ret IDX is equal to half minus IDXi. So this is equivalent to n over 2. And then we say for I is equal to 0. Our condition will be I is less than MD size and ret IDX is less than number of digits, then I plus plus, and the second part of the incremental step will be ret IDX plus plus. So now our global and local terms are within this condition up here. So I is less than MD size is our local check to make sure that we don't go out of the bounds of the middle term. And then ret IDX is less than number of digits is our global check, because in some cases the sum term, just because of the way the indices work and our padding works, our implicit padding works, it may grow beyond the number of digits. However, those will only be zeros, and that is a guarantee. There would be no result that would give us anything above that. But this is just to make sure that because the middle term could have a bunch of zeros at the end, but we haven't trimmed it, so we just have to make sure that we're not going beyond the return array. Alright, so in this case we're going to say ret at ret IDX plus equals MD at I plus carry. And then we want to do our calculate the next carry. So carry is equal to false. Then if ret at ret IDX is greater than or equal to base, then carry is equal to true. We've seen this millions of times. And then ret at ret IDX minus equals base. And then we have to consider the last carry here. That is an obligation. So if carry and ret IDX is less than number of digits, then we're just going to say ret at ret IDX plus plus. So if there's an existing carry and we're within bounds of the return array, then just increment the return, that last digit there. All right, so that's it. Now we just have to clean up and return our values. So free low, free MD, free high. So these were our temporary arrays for the recursive calls. Then we can also free I1 sum, free I2 sum, and then we can output. So dereference outsize and set it equal to the number of digits, and then return a ret. Good shit. And that should be it. Alright, let's open up our terminal, go into main.c. I have an example here. It just multiplies some stuff. We can leave the call as is. So let me just run this. Oh, cp test and then run. I don't know how many digits this is. This is only 3 digits, so this will go along multiplication either way. So let's just blast this with some large ass number. Alright, now let's run this. We didn't get any errors, which is fucking sick. And we got a segmentation error. Segmentation faults. Setting the outsize. What's wrong with that? $775. Okay. This doesn't seem like an algorithmic error. Just this. I'm setting the outsize to the number of digits, but I'm dereferencing it, so it doesn't like that I'm trying to access his memory. But I have to. So I cannot tell. Ooh, no, that's not it. That's wrong. No, we're good. I don't get why this would be an error. Not passing in anything that's not a pointer. Huh. This sucks. I literally have... Let me try running it again. Segmentation fault. We don't free outsize anywhere, I don't think. Alright, so that's the parameter. Okay, that's right. Yep, good. Well, that's our error. Don't know why it's bad though. Outsize is a pointer. Dereference the pointer. Okay, I think it might be this then. It's not liking this. Alright, let me just try something here. I'm just going to try printing. Or, sorry, I need to... $776, and then also down here. I'm just going to print whenever we assign to outsize. 946, 94, whatever, it doesn't matter. Okay, so we have assigned before, or at least once before, but it doesn't like this. This is very irregular. I'm not liking this at all. Oh, we finished the album. That's sad. I really don't know what's up here. Maybe I need to delete that, maybe rebuild it. Nope. God damn it. I have zero clue what's going on here. Alright. Unfortunately, I can't figure, I don't know what's going on here. So I will, me trying to figure this out on stream is not going to be productive, so I'm just going to figure this out right now, but I will end the stream here. But yeah, so this definitely does work because I've tested this exact code on my own and it's worked. So this is probably just some stupid issue. But yeah, so that is Karatsuba Multiplication, the correct version this time. So yeah, that was fun to, I've been working on this for a while. I just recently, I gave up on it for a while, just because I was getting nowhere, but then I figured out what the problem was, and I was just screwing up with these indices here, and then also when doing the increments, I was just screwing up with how I counted. I know it sucks, I can't really count, but yeah, so hope you guys enjoyed, hope you learned something, and I will see you guys next time, whenever that is. Alright, have a good one.